So I said in the last video that we would prove this now, but actually first I want to prove some even more basic, kind of small, useless facts like this. Mainly not because this is useful, but because it would be nice to see that all our definitions are working. So it might just be a nice bunch of practice to start with. So if our definitions are built properly, then things like this should be true. So let's see. Usually our proofs take the form of paragraphs because we have arguments to make, things to say, but this is one of these rare situations where it just ends up being a giant chain of equalities, and each equality has some justification for it. So let me just start with we have, and then I'll write a big chain of equalities. So let's start with the left-hand side, 3 plus 2, and let's see if I can work my way up and unwrap definitions and see if I get 5 at the end. So 3 plus 2. I have no choice now except to use the definition of plus, right? Or the definition of 2 and the definition of 3. I will certainly need those at some point, but the definition of plus. That's definition 111. Plus is defined to be something involving add. So I get 3 plus 2 means add 2 to 3. That's what 3 plus 2 means. So then, so what should I do next then? I need to know, so I've got this function, add 2, and I'm applying it to 3. How can I make any sense of add 2? What function is this? How do I know? Well, I need to use the definition of add. But the definition of add is recursive. So it does not tell me directly what is add 2. Instead, it tells me only what is add 0, and it tells me a recursion rule. So it describes to me add 2 in terms of add 1, and it describes to me add 1 in terms of add 0, and then it tells me what add 0 is. So if I want to do anything from here, then I should use the definition of 2. 2 is defined to be next 1, right? That's the definition of 2. And then the recursion rule for add tells me that add of the next of anything is this. So there I've reduced add 2 to something in terms of add 1 using the recursion rule. And of course, at each step, what I'm doing is replacing something by something that it's equal to, right? In a term. This overall expression is a term, and I'm taking some object in here and I'm replacing it by something that I know it's equal to. Or actually, this is the object, and I'm replacing it by something it's equal to. So that's theorem 4. It's letting us do that kind of thing. Here, this is the object, and then it's getting replaced by something that's equal to. Theorem 4. Okay. Now to proceed, I should probably figure out what is add 1. But I'm not told directly what is add 1. I'm given a recursion rule, so I know what add 1 is in terms of add next, in terms of add 0, right? So I should write down that 1 is actually next 0. So from here to here, I'm using the definition of 1. And then, oh, lost a parenthesis. And then what does this become? Add next 0. I need to use the recursion rule. So here. It's this, right? Then add 0. Okay, finally something that I directly know what it is from the definition. It's the identity. So here I have this composed with the identity. All right, so this was again by the definition of add. This time the starting point rather than the recursion rule. And let's see, I have a few options now. I could rewrite things like this. So when I take this composite and I apply it to 3, I'm really just applying each of these in succession to 3. what would I be using there to do that? Where is it? It's this idea, right? Essence of composition. If you have two functions, you compose them, then what that does to a particular input is that it applies the right-hand function first, and then it applies the left-hand function. And yeah, you read it kind of backwards because you want to be able to not flip these around. Okay, so we have this, and I applied it multiple times, right? So first I had to apply it to get rid of this circle, and then I applied it to get rid of this circle. So now we're here. And then, well, the identity function applied to 3, that's, there are a couple of ways to say what that is. I could say that, well, I'm applying the identity function definition, or more directly, probably better, is to say it's this, since we've singled out that fact that the identity function does nothing to things. So then, using that idea, identity on 3 is 3, right? Great. And then, what does this actually do? It does next, right? That's what it does when you input something, when you input a natural number. So let's do it one at a time. So first I do this, then I input 3. 3 is a natural number because 0 is a natural number, and so therefore so is next 0, so is next that, and so on, all the way up to 3. So 3 is a natural number. That puts it in the domain of this function. So we get next 3 here. The next 3 is also a natural number, so here we get next of the next of 3. So you see how add 2 works? All of this work so far, you can see the 3 has just been sitting there not changing, right? All of this work was just figuring out how to work with add 2 and breaking it down using the recursion rule. And you can see it operates as it's supposed to. Add 2 applies next twice. That's what it should do. Add n should apply next n times. Okay, but our goal is to say 5 at the end, and we're almost there. By the definition of 4, next 3 is just 4, right? And by the definition of 5, next 4 is just a longer name for 5. So, or maybe, rather I should say 5 is a shorter name for next 4. Okay, so that's it. Now, if you write a proof like this, probably it's good to justify, I mean, it depends on the audience and the context, but it might be useful to justify the individual equalities rather than just write equal signs. So if you end up wanting to do that, you could put some parenthetical comments here that explain why each one is true. But since we're talking through it here, I guess I don't really need to. Okay, great. So we have proven that 3 plus 2 equals 5. And it followed directly from the definition of plus, which we just created, and our old definitions of 2 and 3. Now finally, in the next video, we'll establish these basic things. And once we have these things in hand, a lot of things will become easier. We'll be able to kind of throw away our old definitions and mainly use these basic things that we have established.